Next speaker will be from Sweden, Raj, who will speak about the feasibility and the desirability of employing the thorium fuel cycle for power generation.
Oh. And I need. Oh, that's the laser. Okay. Okay. Yeah, I chose this title because I think it's kind of important to look at the feasibility and also look whether there is a market for these. Is there desirable market, or is there desirability on the part of employing the thorium fuel cycle for future nuclear power generation? It's a review paper. It's basically telling about what has been done and what were the considerations, and now let's look at it again and see what possible things we can think of to do in future for thorium fuel cycle. First thing I will tell you that the person who's responsible for you to come to this meeting was a Swedish chemist, Berzelius, who discovered thorium in 1828. He named it for a Norse god of thunder, Thor, and that's why it is thorium. Yeah. Thorium hasn't been used really any place commercially. Only it was used as in gas mantles in Europe, but it doesn't contain any fissile material. And the only thing which is good about it is that if it absorbs a neutron, it becomes U-233, which is a very efficient fissile fuel for thermal reactors. Eta is 2.06, so that's why you can get a light water reactor breeder, which I will talk about. In the 1950s and 60s, breeder development was being pursued in the USA, and that was a plutonium-uranium breeder, a fast reactor. And the plutonium was going to be generated by LWRs, but the future was going to be a fast breeder reactors for an unbounded scenario of growth for hundreds of years. That was the position of the US Atomic Energy Commission. They were not funding anything in thorium at all. But there was also a parallel development going on, which was by Admiral Rickover, and that he was developing the U.S. nuclear navy, and he didn't want to use any sodium in the nuclear submarine, so it was water reactors. And the chief scientist, Dr. Redkowski, who was mentioned by Dr. Rubia, he came up with the idea of developing a breeder reactor with water technology, and that was called the Redkowski reactor design, which I will show you in a few minutes. The LWBR, the light water breeder reactor, was constructed, operated for a few cycles, and did get a breeding ratio of like 1.01, which was the maximum they could get from 2.06. There's some loss of neutrons, and certainly in the reactor. Meanwhile, General Electric Company was developing the boiling water reactor, and Westinghouse developing the PWR, and they were already developed by the time the LBWR was put together and proved itself to be a breeder. Those companies, the vendors, did not want to wait for development of LWBR. The uranium was cheap, $8 a pound, $18 a kilogram, and more was found. So nobody supported the thorium fuel cycle work at that time anymore, because the naval reactor work also stopped after LWBR, and there was only low-level work. And I actually worked on part of it, just for example, for the critical experiments which we conducted with U-233 in Brookhaven lab. Thorium was picked up in other countries like India, which had large deposits of thorium. You heard about it. In early 70s, there were 100 reactors ordered. And then it looked like that the uranium is going to get expensive because you have to assure the supply of uranium for 40 to 60 years. And so then again it led to a revival of some thorium work, and thorium was also considered for fast reactors at that time. But then the TMI-2 happened in 1986, and Chernobyl followed in TMI-2 in 79 and Chernobyl in 86, and then the orders all dried up, and so the pressure on uranium supply decreased very much, and thorium development never got encouraged after that, even with the curtailment of the fast reactor program worldwide. We did investigate thorium fuel FPRs and about cross-progeny fuel cycles in which you generate U-233 in fast reactors and use it for water and heavy reactors to get better efficiency, but no thorium fuel LMFPR was built. Several small-scale reactors with thorium were built. This is important to realize that it was not dead. It was still active to some extent. And I show you the reactors, which this has been shown by earlier too in this earlier session. The first one was Elk River, which is a BWR. Indian Point was a rather large reactor, Peach Bottom, Shipping Port. Shipping Port is the LWBR, and then Fort St. Marine, AVR, and THTR, which is in Germany, and then one small one in England. So these were really a range of reactors, some small and some quite big, really. It's quite big, really. This is like 842 megawatt thermal, 330 megawatts electric. This is THTR was 300 megawatts electric. So they were quite big prototypes. And main thing to see here is that most of these reactors had no problem with thorium fuel. The Elk River operated with 93% 235 and thorium fuel and stainless steel clad, and the plant was shut down because of stress corrosion cracking. There's no problem with the fuel itself. Reactor operation was normal. Also, an Indian Point reactor, they closed it down after one cycle because it was expensive fuel. The Shipping Port reactor, which employed 233, obtained from other plants which were reprocessed. It had a very it was a highly economic design. This is a seed and blanket concept. The seed is with this crosshatch UO2 thorium oxide fuel, and it moves inside a blanket material that there's no control rods in this reactor, and this is a position in which reactivity is down on the right and high reactivity on the left. The seed blanket module, and this was it's a small reactor, 60 megawatt electric, but it was U-233 thorium fuel cycle. And final core, that seed blanket assemblies, there were no safety and licensing issues in this. The cladding was zircaloy, and no safety and licensing issues. Radiated fuel was reprocessed at the NFS plant in New York. Fuel burn-up was not very high, but reprocessing was established, and that the BWR core did breed. They achieved their objective. India has also started irradiating thorium rods and bundles in CANDU-type plants. Thorium-93 percent enriched fuel uranium was in the fuel in Peach Bottom and Fort St. Vrain, and they worked very well too. Fort St. Vrain reactor operated with carbide fuel kernels for 15 years. The plant was shut down due to problems with helium circulators. No problem was found with fuel. The THTR pebble bed released some fission gas, and some pebbles were found to be defective, but it was only few of them, and the TRISOF fuel actually worked very well. This is the layout of the Fort St. Vrain reactor, and they had a blanket, and they had two regions of the core. This table shows you that how many years they operated. Operating life was Elk River 7 years, 15 years for AVR, and 22 years for THTR. Shipping port was for 6 years. This is the LWBR. The only reactor which used U-233 was this shipping port LWBR. The others used U-235, and that was the mixture with the thorium this fresh fuel only handling with 233 was in the LWBR. The others not so. That handling did not involve U-232. Summarizing the experience based on thorium fuel cycle fuel in thermal and fast reactors is relatively meager compared to that of uranium fuel cycle. In all these plants except for LWBR, the core did not reach equilibrium fuel conditions, so that the low value of beta with 233 did not create any safety issues. This kind of issue is also for the plutonium fuel, but the LWBR operators did not report any problem with low value of beta. All the thorium fuel reactors employed open cycle except the LWBR, which recycled U-233 fuel obtained from other reactors. That's the front end of the cycle, but now let's look at the back end of the fuel cycle. We know that the full benefit of the I'm not used to this one. The full benefit of thorium utilization is clearly when thorium fuel when there's a reprocessing, a refabrication. So this work was started in the United States. This is all U.S. work. This LWBR and Indian Point fuel was reprocessed at the NSF plant in New York, and a lot of pilot scale work was performed in Oak Ridge National Lab and B&W. It also was performed, reprocessing was also performed in Hanford and Savannah River. The development work was very active. It was stopped in 1970. But the reprocessing of the fuel from LWR, the process was developed, Haddon process was developed in Oak Ridge National Lab. It was claimed to be ready for industrial application. The cost was not that very high, only 30% larger than uranium processing. The NFS cost for LWBR processing was, as published, as $78 per kilogram of reprocessed thorium fuel. So it's not really that high. And then the refabrication, this refabrication was done in Oak Ridge in a shielded facility. And the reprocessed product is a salt gel which can be directly employed for refabrication. They made 1,000 rods for a critical facility experiment. And this is shown in the next one. This is I actually was doing some of these experiments with these rods, and they could be handled without any problem, no big issue. And this is the whole thing was constructed, and this is called Kilorod facility in Oak Ridge. This is a shielded facility, and that's where these rods were constructed. And the salt gel was prepared, and then it came here, and the rods were made in this facility, which is not very big, but it's with 8.5 inches of concrete all around. And then a fuel assembly for LWR reactors, I mean, was constructed in B&W. This is the finished assembly produced during demonstration. This they did with a rather only small amount of U-232. This was about 42 parts per million, and they could do it without any shielding, and that's what they did accomplish. That if you are able to reprocess and immediately start, constructing fuel assemblies, it can be done. It can be done without really real shielded facility. As long the U-232 into 33 is less than 1,000 ppm, and rapid fabrication can be performed in unshielded facilities. P&W demonstrated that, but and this was 3% U-233 and 97% thorium oxide. It was freshly prepared U-233, and they had 42 ppm of U-232. So all the personnel doses were within the acceptable limits in this case. Also, they found that if radiation dose hazard is much small, if thorium-228 is separated immediately from U-233. And an interesting set of pilot scale tests were performed at Hanford and Savannah River reprocessing plants to produce U-233 having less than 5 ppm U-232. This was also done. They produced 160 kilograms of this U-233. This product can be handled for fabrication with glove box operation as practice for UPO2 fabrication. The Italians constructed a facility called PCOT. This was remotely operated shielded facilities, since it was argued the flexibility to wait between reprocessing and refabrication would be needed. Unfortunately, remote operation had troubles, and the refabrication plant was shut down. And this is the facility which was constructed. It worked. It finally did reprocess the Elk River fuel, but it was not working too well. In terms of irradiation experience, all the thorium-based fuel has to be tested to see that it does work for long-term irradiation. They found that thorium oxide is a more stable fuel. However, it's important to establish burn-up level it can sustain and the duty cycle that the fuel can endure. So this was a long campaign in Oak Ridge National Lab, and there's a table here which shows you the linear heat rating watts per centimeter, and it did go up to about 1,000 watts per centimeter, and it did go up to 100,000 megawatt days per ton of metal, and there's others which are smaller, less burn-up level and lower level of linear heat rating. But quite a lot of work was done. Then it was just stopped. The money stopped on this, and then the work stopped. Now, recently, more work has been done on thorium fuel cycle in LWRs. Thorium used with 28% uranium, U-235, it has been studied in some detail. The uranium requirements are greater if the fuels are mixed together. It's better to have them in separate rods rather than mixed together. Then it's more economical. The U fuel can compete with once-through uranium cycle at burn-up levels of about 120 megawatt days per ton in PWRs. For pressurized heavy water reactors, the competing burn-up level would be about 40 to 50 megawatt days per ton E. So if you do carry it to higher burn-up levels, you can actually compete with the once-through cycle. Homogeneous designs have been studied. Reactor physics calculations have been made, and Rutkowski patented some thorium fuel designs. The seed blanket concept can be incorporated in a square PWR assembly called SPU, or separate seed and blanket assemblies. These are I first show you this graph, which is the fissile material requirements versus discharge burn-up, and this shows you that as you go to 80,000 megawatt days per ton, you're really almost flat, and the requirement is much lower than when the burn-up level is low, and this is with plutonium. So both these graphs show you that indeed it is much more economical to and you can compete with the ones through uranium cycle. These are the configurations. This one is really like a seed blanket in a PWR assembly. This is a all blanket, and the next shows you this arrangement of assemblies. This is the top one is a seed blanket assembly, and this is like that, and they are each bundle is like seeds and blankets around. Okay, and then this is the other one in which they are in separate assemblies. Now I want to look at desirability. We can enumerate the advantages and disadvantages. Advantages is U-33 is a very good fuel. It's the best fuel. Thorium oxide has better stability and conductivity than U2. Thorium will not produce long-life actinides as many as U-238. Waste volumes will be smaller. Thorium is excellent for burning plutonium in both thermal and fast reactors. Radioactive U-233 and thorium provides resistance to proliferation. High decay of heat of plutonium if medium enriched U is used. Also resistance to proliferation. Much to U-233 form can be burned if high burn-ups are achieved. Thorium oxide should be cheaper than U2 on world market. Thorium is more abundant. And of course, there are disadvantages too. No fissile isotope. U-232 to produce makes fabrication difficult. Enriched MEU will produce decay heat, making storage and disposal more difficult. Thorium produces protactinium, 27-day half-life. This requires greater shutdown requirements for 3 months of outage. U-233 and plutonium produce beta 0.3%, which is faster transients. Control rod and soluble boron words are decreased. The seed blanket configuration imparts better exploitation of advantage of thorium, but has thermal hydraulic design issues. All the above advantages and disadvantages are known. Were known for many years. This has been demonstrated that the disadvantages can be designed around. The disadvantage of U-233 in the back end of fuel cycle can be dealt with by using remotely operated shielding facilities. Compensation can be obtained by greater efficiency of U-233 and the potential for higher burn-ups with thorium oxide. Most important would be the magnitude of cost advantage of thorium oxide over U-2 as the raw fuel. What is the cost differential? In the past, it did not make much economic sense to consider thorium fuel for larger scale application, since we thought that we're going to use plutonium and fast reactors, but later on that is dropped. In the current situation, what happened now? Can we go back? No. Can you go back?
For your last minute, we will try.
Yeah. No, it doesn't. You need to.
Stuck.
It's stuck.
So maybe on the.
Then let's go. Yeah, I can go fast out.
Let him do.
Okay. Keep going. Yeah. And in the current situation, really, the LWRs are the king. Nobody is constructing any fast reactors. Nobody has any real MSRs, molten salt reactors. And the life of LWRs has been extended from up to 60 to 80 years. So this is really the action now. The vendors are there. There's no vendors for anything else. So I think right now the main thing is that we have to consider that we have to give a different mission to mission of disposal of accumulated plutonium should be justified for thorium. I think this is important to do because thorium cycle provides an efficient platform to burn and transmit plutonium-239 in light water reactors or fast reactors. U-233 form cannot be easily used for weapons manufacture. That's a non-proliferation argument. So long burn-up of plutonium-thorium also burns the U-233 form, so thereby producing additional energy. So these are good points for thorium. But it needs a further justification to have the governments interested. In this, I think this is the justification to be made for thorium. In future, when fuel cycles are close to U-233 made in plutonium-thorium fuels, LWRs or fast reactors could be extracted and employed for power generation LWRs. This would require shielded facilities, but by that time, all the calculations on economy could be different. So I think that's important. Research and pilot-scale development for thorium cycle need public financing. If governments assume that responsibility, commercial use could become feasible and desirable.
Okay. Thank you very much. Thanks for this nice conclusion. And the paper is open for discussion. Please, go ahead.
I was wondering if you'd be willing to expand a little bit on the economic benefit of having separate thorium and uranium fuel kernels or fuel pellets. And then the extension of that, what is the physics impact of doing that?
Yeah, that has been demonstrated with reactor physics calculations, that indeed this is much better, much less U-233 is required, much less U-235 is required to get the reactor going. Of course, the issue is that you have to have separate channels of thermal water coming in for all these different bundles, because the bundles which contain only thorium and then with the others which contain only seed, they generate different amounts of power. So there's a thermal hydraulic issue at the moment. So that core has not been put together either. No, not really. There is not that much incentive with the vendors to go in a different route at the moment. Yeah.
Okay, that's also a very clear assessment. Yes, please.
No, just my question is regarding your recommendations. I mean, I think you're a little bit biased towards light water reactors. Even after Fukushima accident, one of the major issues of light water reactors is kind of that use of water as a coolant, which has a multi-phase component. Yeah. Instead of that, what do you feel about the recommendation of the thorium particularly for the high-temperature gas-cooled reactors? Because now it has been demonstrated in the past, and it is showing some revival of this, because the similar situation to the Fukushima, perhaps could not happen because of the rest heat stored in the reactor because of the high.
But there are 430 light water reactors in the world.
And that is true.
And only one or two, not even one maybe. And there's a lot of experience. We have hundreds of thousands of safe operation years too, Now the Fukushima has happened. It has really created a very bad situation. But I think it has also led to increased safety for light water reactors since that time. it has led to increased safety, and the new designs in particular. You know, that was a 40-year-old design. This new designs for like, you know, EPR and AP1000 and others, they are much better in terms of they deal with the core melt. So you cannot just say that because of Fukushima, all the LWR development is going to stop.
Okay, let's close the discussion there.
Yeah.
You see 0-0.
Yeah, okay.
But thank you for this last comment, which I think was actually quite important comment. And let's